Okay, let's start by solving the quiz. So this is really not too different from what we have done previously. But looking at your quiz solutions, I see a great level of panic. Okay, a lot of you are just panicking because it's something new. I'm asking you to find the frequency of the oscillations. But please do not, you've learned some valuable tools. Please do not throw them away. How do we solve any mechanics problem? We look at free body diagrams. From free body diagrams, we apply Newton's second law. Now the new trick, on top of all this machinery, once we have the dynamical equation F equals ma, we want it in a particular form, the differential equation that we want to solve. Okay? So that's what I'm going to do. I have two springs tied to two opposing walls and the mass between them, so I'll actually assume at some instant that my mass has moved by a distance x. When it has moved by a distance x, what are the forces on it? The first spring will give me a force that's trying to restore me to my original point. How about the second spring? It's also going to push me in that direction. So if I look at the free body diagram, here's my M. There is F1 and F2, both in the same direction. What is the magnitude of F1? The first spring is stretched by an amount x, so it's going to be k times x. How about the magnitude of F2? The second spring is compressed by an amount x, so its magnitude is also kx. But I chose x to be in the positive direction, so what is m times a, which is m times d square x dt square? It's going to be minus f1 magnitude minus f2 magnitude, or minus 2kx. Why the minus sign? Because it's opposite to the direction of x, right? The forces are trying to restore me to x equals 0. So what's my equation now? M times d square x dt square is minus 2kx, or d square x dt square is minus 2k over m times x. Is that the differential equation I know how to solve? That's my one and only dear differential equation, right? So I know that the solutions are going to be C1 cosine omega t plus C2 sine omega t. And the question is asking for the angular frequency, so I just need to find what's omega. If I take two derivatives of this, I'll just have minus omega squared times C1 cosine omega t plus C2 sine omega t. I chose these functions because taking two derivatives of them is basically getting a minus sign times the constant. So now I can actually plug this into my differential equation. What I will find is omega square is 2k over m, or omega is square root of 2k over m. So essentially what I'm saying is do not panic. Okay. Proceed as usual. Try to do your free body diagrams, find the acceleration. The only thing as a next step is once you have F equals ma, if you're trying to find the small oscillation frequency of any oscillator, you should try to get it back into the harmonic oscillator differential equation. All right? Let's solve one more example. If I have a rod of length L which is pivoted from its one end under G. Okay, so this is basically, my hands have too much friction. I can't swing this nicely. So basically, I would like to understand what kind of motion this pen does if it's pivoted from one end. Okay, what's the frequency of its oscillations? Now, how do I do this? Just as usual. Okay, don't panic. So I'm asked to find omega. Let's look at just any situation where the rod is making an angle theta with the vertical. Now, what are the forces acting on the rod? It will have its weight, mg, and that is acting from the center of mass, right? So it's going to be mg, and this distance is going to be L over 2. What else? What other force is there? There must be some reaction force so that this rod does not fall down. So let me call this the normal force. But does that normal force give me any torque? No, it's exactly applied to the pivot point. So what do I need to do? I need to basically calculate the torque due to mg. So torque is R cross F, or R magnitude F magnitude times sine theta. And here is my triangle. R sine theta is, well, L over 2 sine theta, right? F is mg. So torque is mgl over 2 sine theta. Which way is this torque trying to rotate my rod? Is it clockwise or counterclockwise? It's clockwise, right? It's into the screen. So this is clockwise. How about the angle theta? Theta is increasing counterclockwise. So when I write my Newton's equation, which is torque equals I alpha, torque is mg L over 2 sine theta. How about I would remember that the moment of inertia from the edge of the rod is ml square over 3. ml square over 3 times alpha is d square theta dt square, but theta is counterclockwise, torque is clockwise, so I have to be careful. I have to put a minus sign on one of those quantities. Okay, good. So 1 power of m cancels, 1 power of L cancels. I have d square theta dt square is minus 3 halves g over L sine theta. Is that the differential equation that I can solve? Not yet. Not yet. This is not harmonic differential equation. So I should only answer for small oscillations. So when I have small oscillations, small oscillation means sine theta is almost theta. In other words, when I had this function sine, I could approximate it by a line. Okay? In that case, d square theta dt square will be minus 3 halves g over L theta approximately. And now, this is the differential equation that I can solve. I know that if I have this form theta of t is going to be C1 cosine omega t plus C2 sine omega t. And if I take two time derivatives, I'll just get minus omega square theta of t. That's what sine and cosine functions enable me to write. And if I plug these into my differential equation, I find omega square is 3/2 g over L, or omega is square root of 3/2 g over L. Okay? Does that? Let's check units. I haven't checked units in a while. What's the unit for g? Meters per second square. What's the unit for L? Meters. The unit for omega is 1/seconds. So it does make sense. Okay? It's good. Now, such an object is actually given a name. If I do not actually have just a mass swinging from a rope, for some reason it's called the physical pendulum. And you see, I could actually do this for an arbitrary object. If I had some, arbitrary object, I take this object. I'm trying to use this as a pendulum. I'll fix some pivot point and then look at its oscillations. Okay, I can always do that. What's the equilibrium situation? The equilibrium situation is, here I have my pivot, and the vertical line passing through the pivot must pass through the center of mass. Okay. Let's say that I know what the center of mass moment of inertia is. I also know the distance d from the center of mass, and I know the full mass of this object, m. Let's try to figure out the frequency of small oscillations of this pendulum. Well, here's the thing. I need to consider all this object rotated by some angle theta. So I'm not going to be able to form the same object, but here is my pivot point. Now, this is the vertical, and now the center of mass, the line from the center of mass to the pivot makes an angle theta. Now, what is creating a torque? What is restoring my object to its original position? Gravitational force, which is mg, and for a rigid body, mg is as if it's acting at the center of mass, right? So I can show it that it's acting on the center of mass. So this distance is d. What is the torque? Torque is r cross f. So it's going to be d times mg times sine theta. Theta is increasing counterclockwise. My torque is clockwise. Theta is counterclockwise. So I alpha is equal to torque. But what is I around this pivot point? If I know I center of mass, there was the parallel axis theorem, m d square. So now I can write I center of mass plus m d square theta dt square is minus, because clockwise and counterclockwise are opposing directions, d m g sine theta t square t square is minus d mg over I center of mass plus d square times sine theta. Once again, that's not a differential equation I can solve, but for small oscillations, sine theta will always be almost theta, so d square theta dt square is minus d mg divided by I center of mass plus d square times theta. And now that's a differential equation I know how to solve. It's going to be C1 cosine omega t. Wow, that's pretty interesting. Plus C2 sine omega t. I think it was 2 years ago. For some reason, I decided I should prove the parallel axis theorem in class. And I did the proof. It took around 15 minutes. And just around at the end, I said, so you see the parallel axis theorem is correct. And the whole class went, ah. I was very impressed by myself. Well, apparently, you know, just the projector went out. So that was why the people were sighing. But now, the nice thing about this form is d square theta dt square is minus omega square times theta. So essentially, in my differential equation, I can just write omega is square root of d mg divided by I center of mass plus d square. So that is the most general result for a physical pendulum. Okay. Let's check the units because this looks like a complicated expression. D has units of, let's look at the units of that, square root of, unit of D is meters, m is kilograms, g is meters per second square. How about the unit of moment of inertia? It's always ml square, mr square, so it's kilogram meter square. Nice thing is that kilograms cancel. This is 1 over second. It actually checks out. But that basically tells you you should be able to calculate the oscillation frequency of any physical pendulum. Okay? Once you know what? You know the moment of inertia around the center of mass and the distance of the pivot point to the center of mass. Okay? Now, here's an interesting piece of information. For a very long time, our standard unit of time was based on a physical pendulum. It's called the Cater's pendulum. If you take a rod, you'd find 2 points for which the oscillation frequency is the same. So you pick a point along the rod, you look at oscillations, you pick a other point on the other side of the center of mass, you look at the oscillations. If the 2 oscillation frequencies are the same, then that oscillation frequency only depends on the distance between these 2 points, not the distance to the center of mass. So that distance can be measured very accurately. And for a long time, our standard second was based on a pendulum, actually, on a physical pendulum. But so that was the way to define the unit before people could do atomic spectroscopy. Okay. Good. Let me solve one more example. And hopefully, now, I'll teach you also some mathematics. Now, let's do the following. Let's say this is a bead on a frictionless wire. And it's tied to a spring which is a distance d away, and the relaxed length of the spring is L. Okay? Find the frequency of small oscillations. So what am I actually wondering? If I move that object a little bit, I know that it's going to oscillate back and forth, right? That's what my physical intuition tells me. So what I would like to find out is what is the frequency of these oscillations where the amplitude is very small. So is there any need to panic? No. If I ask you to find the acceleration when the distance from its original point is x, you would be able to do that. So let me redraw this. This distance is d. So my original position is that this is L. I'm not drawing the spring. I'm just looking at the distance. Now I have moved by a distance x. Right. So I need to find the new length of the spring, right? So what's the new length of the spring? L prime is what? Well, I have geometry which tells me that this distance is L squared plus L squared minus d squared square root. So L prime squared must be what? L prime squared must be square root of d squared plus square root of L squared minus d squared plus x squared. You're right. L prime is equal to that. Okay? Now, if that is the length of my spring, what is F, the force, the magnitude of the force applied by the spring onto my mass? It's going to be K times L prime minus L. How about the x component? Fx is going to be, if that angle is theta, it's going to be F cosine theta. So let me write that Fx magnitude is K times L prime minus L times. How about cosine theta? Cosine theta is square root of L square minus d square plus x divided by L prime. So that's good. L prime minus L times cosine theta is square root of L minus L square minus d square plus x divided by L prime. So what's my differential equation? f is equal to m times a. So m times d square x dt square. Because f of x is moving in the opposite direction to f, it's going to be minus k times L prime minus L square root of L square minus D square plus X divided by L prime. Right? Can I solve this differential equation? Yes. Come on. I don't think there's actually a general solution for that. Okay, it's too complicated because everything L prime here also depends on x, right? So here is this m d square x dt square is minus k. I'll just write it in full glory so that anyone who is not in class and looking at the class notes gets intimidated. Okay, that's just to scare people who are not showing up for lectures. So I'll write it square root of d square. It's going to be so long they'll just give up on the course, okay? L square minus d square plus x squared minus L. That's L minus L prime, right? Good. Then I have square root of L square plus minus d square plus x divided by the same thing again, square root of d square plus L square minus d square. Would you give up on the course if you saw that in lecture notes? Good. Now, that is not a differential equation any sane person is going to try to solve. Okay? But here's the thing. I'm looking for small oscillations. Okay? Here is my function. Let me call all of this some function of x. Okay? Now, that's going to be a complicated function. But can you tell me what is the value of f at x equals 0? Come on, look at that L prime minus L. L prime minus L is 0 if x is 0, right? What I have on the right-hand side is exactly the force when I'm in equilibrium position. In equilibrium position, I don't have any force, so that's 0. Now, I know that f of x as a function of x is going to be some complicated function. I'm just making it up. Okay, complicated function. But for small oscillations, maybe I can make a linear approximation to it. I can say, hey, if my oscillations are small, it's going to be in that small region. So my approximation is going to be correct. Now, I can see some of you are not too happy with it. But it turns out that basically is telling you how you define a small oscillation. All right? How do I make a linear approximation to any function? I should make sure that the slope of this line is equal to the slope of my function at 0. In other words, f of x should be the value of f of x at 0 plus what's the slope of f at 0? F prime. So it's basically df dx at x equals 0 times x. Plus there are higher order terms which I neglect. Yes. Let me explain it again. So I have some function f of x. And if it's on the right-hand side of my differential equation, I have no hope of solving it. Thankfully, the question asks me to find small oscillation frequencies. So I'm going to make a linear approximation. You remember the sine, right? I can't solve it with sine, but if it's a line instead of sine, I can make an approximation. So I'm saying I can do that linear approximation for any function I have. Okay? How do I make the linear approximation? I'm saying, hey, here is my function. I'm going to make it a linear approximation, which means I should choose a slope, a line, so that the slope matches the slope of function f at 0, at the point I'm making approximation. That's why I'm saying f of x, when x is very small, equal to its value at x0 plus its derivative times x. Okay? Now, the systematic method of doing this, you're going to learn approximating a function around a point, you're going to learn in calculus. It's called Taylor series. But it's okay if you don't know. We just need the first term. In general, what we're going to see, what you're going to learn is that f of x0 plus del, okay, let me not go to partial derivatives, df dx at x0 times x minus x0 plus 1 over 2 factorial, the second derivative of x at x0 times x minus x0 square. So you have higher order terms, but we are not interested in that. We just want to, and we're very humble. We don't want to solve the general differential equation. What I actually just need is the derivative of that at x equals 0. Okay? So let's do that. So I will use the tools of technology to hopefully save some time here. Good. I'm not sure if I saved any time, but so that's my f of x. So I'd like to take the derivative of this function. Okay? Now, that's what I'll do. df dx. Let me take the derivative of the first term. L is just a constant, so I need to take the derivative of what's here, 1/2. Inside that is 2, x is that. So square root of L square minus D square plus x divided by the square root again. I'll not write the square root times this whole thing. L square minus D square plus x divided by the square root. It's always the same square root, right? Plus, I'll have the same thing, square root minus L. Now I need to take the derivative of what's here. The derivative of that is derivative of the numerator times the denominator minus L square minus D square plus x times the derivative of what's inside that square. It's going to be 1/2 times 2 times square root of L square minus D square plus x divided by the square root divided by that square root square. All right? Once I don't write the square roots, it's actually not too hard. But what happens, I actually need the value of df dx at x equals 0. So what should I do? I'll just put x equals 0. When I put x equals 0 into my square root, what is the value of the square root? When x is 0, it's just L. So that's very good. I can just write minus K times 1/2 times 2 times square root of L square minus D square. I put x equals to 0. So that becomes L times L square minus D square square root divided by L minus K times the second term is L minus L, which is 0. So I don't even have to consider all these remaining things. Okay? So it's actually not too bad. This apparently df dx is minus K times L square minus D square divided by L square. So now what is my differential equation? Now m times d square x dt square is just that factor times x. Okay? Can I solve this differential equation now? Of course, it's my favorite differential equation. The only equation you know how to solve. So x of t must be c1 cosine omega t plus c2 sine omega t, which means omega square is what I have here. Let me even write it as follows. Right, that's much better. Minus k over m, minus is gone, d square over L square, or omega as this. Now I solved this example for a very particular reason. Okay, any function, it turns out, for any oscillator, small oscillations are harmonic. Why? Because any function can be expanded in a Taylor series. Now, if there are any math majors here, they are free to object. It's not automatic, right, that a function can be actually expanded in a Taylor series. It can be approximated by a line. If the function has a discontinuity, then you can't do that. If the function actually has a discontinuous derivative, you can't do that. But most of the functions we are interested in physics have this nice property of being smooth. So I can actually have derivatives, which means I can do my harmonic approximation. Let me spend a few more moments talking about general properties of oscillators. In general, okay, if you have your potential energy as a function of x, what are the interesting things you can have? You can have peaks and valleys. What are the equilibrium positions when you have a profile of your potential energy? What was the definition? What was the relation between force and potential energy? Force was minus d v of x dx. What is the equilibrium position? Equilibrium is force is equal to 0, which means dv dx is 0. So equilibrium positions are where my function has a maximum or a minimum. I don't think there is a maximum or minimum there. So, but there are two different kinds of equilibrium positions. If I'm at the top of a hill, if I actually give this mass a little bit of displacement, what will happen? It will just fall down the hill, right? It will actually try to go and sample places where there is lower potential. So such a point is called an unstable equilibrium. if I'm at the minimum of a potential, if I actually give a small displacement to my mass, it actually keeps oscillating, right? If my system tries to come back to its equilibrium position, that's called a stable equilibrium. Another stable equilibrium is over here. So the nice thing is, whenever I have a stable equilibrium, I can essentially approximate the potential by a parabola. So it's like 1/2 kx squared. There is an effective spring constant coming in. And that is my harmonic approximation. So essentially, that's why these small oscillations are important. At any stable equilibrium point, around any stable equilibrium point, there are small oscillations. And those small oscillations actually tell you how stable that point is. If you try to calculate small oscillations around an unstable equilibrium, you do not find small oscillations. You do not find sine or cosine. You actually find sine hyperbolic or cosine hyperbolic. Do you remember what those functions were? They were exponentially increasing functions. It tells you that you're going away from your equilibrium point. And that's actually, once you, let's say, there are no civil engineers here. There is no civil engineering at Bilkent. But when a civil engineer actually designs a bridge, the first thing he looks at is that the system is in equilibrium. But now he also has to check that it's a stable equilibrium. Okay? So what does he do? He looks at all the small oscillation frequencies. If all small oscillation frequencies are positive, then he is sure that he has actually built a stable bridge. Okay? That goes for all kind of oscillations. So that's why small oscillations are important. Let me tell you one more thing. Let me tell you what we're going to do next time. All the trouble we went through, we've only looked at one kind of oscillations. Our oscillations all were energy conserving. So what happens if there is friction? So the next time we'll look at damped oscillations, which means my mass, oscillating mass, is losing some energy. Okay? See you in 2 days, 3 days.